Welcome back to the Deep Dive. We're the place you come to get up to speed fast on, well, complex tech infrastructure topics.
That's the goal.
And today we are tackling a really big one, mobile DevOps, specifically for the iOS world. It can feel notoriously tricky.
Oh, absolutely. If you've ever seen teams just seamlessly releasing great mobile apps, really fast, and they seem immune to all that chaos, like App Store rejections or certificates expiring.
Yeah, how do they do that?
Well, you are probably seeing a really mature mobile DevOps process in action. So our mission today is basically to lift the hood on that entire process.
Okay, so we want to show you, the listener, the foundations, the culture, the pipeline itself, key tools like Fastlane, and crucially, those feedback loops. We're talking automated testing, smart delivery, real-time monitoring.
Right. Everything that makes those rapid, reliable iOS releases actually happen.
It's meant to be a complete roadmap, something to get you genuinely fluent in how this mobile release cycle works, and quickly.
So let's start right at the beginning, the foundation. When we say mobile DevOps, we're not just talking about buying some tools.
Right, it's more fundamental.
It really is. It's a philosophical shift, a cultural one. It's about applying those established DevOps principles, communication, collaboration, lots of automation, continuous feedback, but applying them to the unique and, often frustrating world of mobile app development.
And the goal of all that effort, what's the output?
Continuous integration, continuous delivery, and really comprehensive monitoring. For both iOS and Android, ideally. It's about making sure quality is built in from the start, not just tested at the end, and getting those high-quality apps out faster.
You mentioned the frustration factor. That seems key. How does mobile DevOps differ from, say, the traditional web DevOps world? Because web seems so much faster sometimes.
Yeah, that's a huge point of contrast. In web development, you're usually targeting cloud platforms, right? Servers you control. And you can often achieve instant continuous deployment.
Push code, it's live.
Yeah.
Milliseconds later.
Exactly. Instant gratification.
But wait, is that always good? Doesn't that speed sometimes mean maybe less rigorous testing? You could argue the forced pause Apple imposes, the review, actually forces a beneficial rigor on mobile teams, right?
That's a really critical insight, yeah.
Yeah.
While web releases can be lightning fast, mobile introduces these constraints that basically dictate a longer, more structured release cycle. Your target isn't your own server, it's the App Store or the Google Play Store.
The gatekeeper.
Precisely. This external gatekeeper, that mandatory review and approval, it means pure, automated, continuous deployment straight to the public is, functionally impossible for most apps. It slows everything down.
Which, like you said, forces teams to double down on stability and testing before they even think about submitting.
Exactly. It makes that CI/CD pipeline leading up to the submission incredibly vital.
Okay, so let's map out this unique terrain. Beyond the App Store hurdle, what are the big structural challenges that are really just specific to mobile development?
Our sources consistently highlight 4 main pain points. These really define the mobile landscape. First, and maybe the most obvious, is multiple platforms.
Yeah.
You're almost always dealing with 2 completely separate, very opinionated ecosystems, iOS and Android.
Right. Different SDKs, different tools.
Totally different. Xcode versus Android Studio and Gradle. Swift or Objective-C versus Kotlin or Java. And critically, this often means entirely separate CI/CD pipelines, separate testing strategies, separate deployment constraints.
So right off the bat, you've doubled your infrastructure complexity.
Pretty much. Okay, second challenge. The App Store constraints we just touched on. This isn't just a time delay. It means dealing with complex metadata rules, constantly changing review guidelines, and navigating Apple's whole security and privacy framework. It's a moving target. Third is device fragmentation. And this is way beyond testing on 5 major web browsers. You have to ensure your app works across this huge, constantly shifting matrix of physical devices, different OS versions. iOS 16 behaves differently from iOS 17, sometimes various screen sizes, resolutions, even different chipsets and memory capacities.
You mean like testing on an old iPhone SE versus the latest Pro Max?
Exactly. You have to account for memory constraints on older hardware that, a developer working on a brand new M3 Mac might never see locally.
Which brings us to maintenance, right?
Yeah.
If I push a hotfix, I need to know who's actually getting it.
And that's the fourth challenge, version management. unlike a web app where everyone just refreshes and gets the latest version.
Right, and everyone's on the same page.
In mobile, users update whenever they feel like it or when their device forces them. So you absolutely must be able to support and manage multiple app versions live in the wild simultaneously. You've got the main one in production, maybe another in test flight for beta testers, plus several feature branches being tested internally.
And each might need slightly different configurations or backend support.
Precisely. So successfully doing mobile DevOps is really about building an infrastructure that systematically manages, verifies, and kind of tames the chaos caused by those four big challenges.
Okay, let's nail down the core automation concepts that form that infrastructure. We hear CI and CD all the time. We need to be crystal clear what continuous integration, or CI, means specifically for iOS.
Right. CI is the practice, the discipline, really, of automatically triggering a build and running a whole suite of tests every single time a developer commits code to the shared repository, like immediately.
So what happens in that trigger?
Key activities fire off right away. Automatically compiling the app using Xcode build tools, running all the unit tests, those check small, isolated pieces of logic.
Like a single function.
Exactly. And then running automated UI tests, which actually simulate a user tapping and swiping through the app's interface.
So CI is that instant quality check, the safety net. It answers the question, did the change I just pushed break anything for anyone else?
Perfectly put. And the huge benefit is catching bugs early, like super early, which saves enormous amounts of time and therefore money. If a bug gets caught by the CI server within minutes of the commit,
Easy fix.
relatively cheap and easy to fix, yeah. The developer still has the context fresh in their mind. But if that same bug slips through and only gets found by QA testers days later, or worse, by users,
The cost just explodes. Debugging time, release delays.
exponentially, yeah.
Okay, CI is clear. Build and test on every commit. Now let's tackle CD. You mentioned two flavors, continuous delivery versus continuous deployment. We already established that pure deployment is rare in mobile, but let's really understand why delivery is the standard.
Okay, so continuous delivery means your automated pipeline does everything up to the final release. The CI part runs build, unit tests, UI tests. If all that passes, the pipeline then handles code signing, packages the application that's a .IPF file for iOS, and stages it, ready for release.
Ready to go, but waiting for a green light.
Exactly.
Yeah.
The app is fully prepared, tested, signed, packaged. But there's a manual step required. Usually someone like a release manager or product owner clicks a button to actually push that build to beta testers on test flight or to submit it to App Store Connect for review.
It's that state of readiness that's the key part of delivery.
Yes. Now, continuous deployment, in contrast, means every single build that successfully passes all the automated checks gets pushed automatically to the next stage, maybe even production, with zero human intervention.
Which sounds great in theory.
But because of that mandatory App Store review process, true, fully automated, continuous deployment directly to the public App Store just isn't really a thing for mobile apps. You can continuously deploy to internal testing groups, maybe.
But not to end users automatically.
Right. So continuous delivery, automating everything right up to that final manual submission gate. That's the practical, achievable, and frankly, the standard model for high-performing mobile teams.
Okay, that distinction is crucial. Let's unpack the actual blueprint now. Before we dive into specific tools and vendors, let's understand the structure. What are the core components, the essential stages of a reliable iOS CI/CD pipeline? What sequence does every code commit ideally follow?
Yeah, we can break down a typical solid pipeline into about 7 logical essential stages or components. First, you need the trigger. That starts with the source code repository, usually Git, hosted on platforms like GitHub, GitLab, Bitbucket. This isn't just storage. It defines your branching strategy. Are you using Git flow, GitHub flow, trunk-based development? That choice impacts how triggers work.
And the trigger is usually a push or a pull request.
Exactly. The moment code hits a specific branch or a PR is open, boom, the trigger fires.
Okay, stage 2, the conductor of the orchestra.
That's the CI server or automation tool. This is the brains of the operation. Jenkins, GitHub Actions, Bitrez, Circle CI, GitLab CI, whichever one you choose. It reads your pipeline configuration file, usually written in YAML.
Right, those config files.
And it orchestrates the whole workflow. It tells the build environment what steps to run, in what sequence, using which parameters or secrets. Third stage is the actual build system. For iOS, this means invoking the Xcode command line tools. Xcode build. This component pulls down the source code, resolves dependencies using CocoaPods, Carthage, or Swift Package Manager, compiles all the Swift and Objective-C code.
And the tricky part.
And critically, it handles the complex, often painful requirements of code signing. It needs access to the right certificates and provisioning profiles to create a build that can actually run on a physical device or be accepted by the App Store. It also usually handles version bumping here.
Okay, so once it's compiled and signed, we need to verify it actually works. Stage 4.
Automated testing. This is where the CI server executes all those tests we talked about: unit tests, integration tests, automated UI tests, maybe even snapshot tests to check for visual regressions.
This isn't just checking if it builds, but if it behaves correctly.
Precisely. A failure in here should immediately halt the pipeline. No point deploying something broken. This prevents faulty features from ever reaching testers or users. Component 5 is artifact management. Now, this sounds simple, just storing the .ip file, but it's more involved.
How so?
An artifact is the final verifiable output of your build process, the signed, versioned application package. Good artifact management means storing this .ipa securely, tagging it clearly, like with the git commit hash and build number, and having retention policies.
Why retention?
Well, you might need to keep specific builds that were submitted to Apple for, say, 90 days for compliance or debugging. You need to be able to instantly retrieve the exact build that corresponds to version 1.2.3 submitted last month. Mature DevOps needs this traceability. JFrog Artifactory or just using the CI platform's artifact storage are common here.
Got it. Traceability. Okay, component 6 is actually moving that artifact somewhere useful.
Right, that's the continuous deployment or delivery stage. This step uses automation tools, often Fastlane, or built-in steps in the CI platform to interact directly with Apple's deployment systems.
So talking to Apple's servers.
Exactly. Specifically, uploading the .ip artifact to TestFlight for beta testers, or uploading it to App Store Connect and filling out the submission details for the final App Store review. This removes a huge amount of manual clicking and potential errors. And finally, the 7th component, you can't forget notifications and reporting. A silent pipeline isn't very helpful.
Need to know if it worked or failed.
Immediately. This stage sends alerts, Slack messages, emails on build success or failure. It tracks deployment status. And ideally, it integrates with your monitoring tools, so as soon as a build hits test flight, you start actively watching for crash reports and performance issues from that specific version. It closes the loop.
That structure really clarifies the flow. Let's zoom back in on stage 3 for a moment, the automated building itself. Why is dedicating potentially expensive macOS hardware, whether physical or cloud-based, just to CI builds so important? What are the real day-to-day benefits for a developer?
Oh, the value is huge. It's all about reducing risk and freeing up developer time, basically increasing team velocity. First off, you catch build errors early, instantly. I remember this one time, a junior dev added a new library using CocoaPods, but forgot to commit the updated podfile.lock.
Classic mistake.
Right, on their machine, it built fine because they had the right version cached locally. But the CI server, which always starts from a clean state, failed immediately, couldn't resolve dependencies.
Saved hours but it works on my machine. Debugging.
Exactly. That Slack notification from the CI server, pointing right at the commit, saved potentially hours of team-wide confusion. That's the first big win.
It just kills that whole class of problems.
Completely. Second benefit, consistency across machines. By forcing every single build that matters, like for a release branch or PR to happen on a standardized, pre-configured CI machine.
Running the exact same macOS version, Xcode version.
Same dependencies, same environment variables. You eliminate all that chaos from slightly different local developer setups. The team gains confidence. If the CI build passes, the code itself is solid, regardless of whose laptop it came from. Third, it provides faster feedback, and it's contextual. Developers get a report, often linked right in their pull request, showing the success or failure tied directly to their specific changes. They can fix issues immediately while the code logic is still fresh in their head.
Instead of days later when they've already moved on to something else.
Right. It drastically cuts down the cost and time of fixing things.
And all this automation underpins the whole CI philosophy.
Absolutely. It supports continuous integration. Without reliable, automated building triggered by every push or PR, CI is just a nice idea on paper. Automated building enables those mandatory quality gates, ensuring only code that builds, passes tests, and meets standards ever gets merged into your main or release branches. And if we connect this back to the bigger picture, the choice of which CI/CD platform you use really influences your team's flexibility and, maybe more importantly, how you handle the overhead, especially around needing macOS build machines.
That's a key strategic decision, isn't it?
It really is. Teams have to weigh how much control do we absolutely need over the build environment versus how much maintenance hassle are we willing to put up with or pay someone else to handle.
Perfect transition. Let's dive into the platforms themselves. We have to start with the old guard, the workhorse, the self-hosted standard where you control everything.
Jenkins, yeah. It's been around forever. It's open source, incredibly powerful. For iOS, the main strategic advantage is that it's highly customizable. You can basically script any kind of workflow you can imagine. Total flexibility.
Total flexibility. And there are thousands of plugins for integrating with almost anything. You own the entire process end to end. But that self-hosted nature comes with some serious baggage for iOS. The maintenance overhead is significant. You have to physically source, set up, secure, maintain, and update the actual Mac machines needed to run Xcode builds.
The infamous Mac mini farm in a closet somewhere.
Pretty much. Or Mac Pros if you need more power. Scaling means buying more Macs, networking them, managing OS updates, Xcode updates, ensuring they don't overheat. It's a whole infrastructure job in itself.
This sounds like a hidden cost center, not just an automation tool.
It absolutely can be. And managing parallel builds means managing multiple Mac agents. Plus, the initial setup is notoriously complex. You need real expertise to install Jenkins, configure the right plugins for iOS, secure it properly, and manually handle getting certificates and provisioning profiles onto each and every build agent machine. It's a steep learning curve. Okay, so Jenkins is powerful but demanding. Let's shift from owning the hardware to renting it in the cloud. What about the modern approach? Tightly integrated with source control. GitHub Actions.
GitHub Actions has become incredibly popular, especially for teams already on GitHub. Its biggest win is the native GitHub integration. Your workflows are defined in YAML files right alongside your code in the .github workflows directory.
So configuration lives with the code.
Exactly. Triggers happen automatically on pushes, pull requests, tags, whatever you define, with almost no external setup needed. It's super fast to get a basic pipeline running. Plus, and this is huge for many teams, it offers hosted macOS runners. GitHub manages the Mac infrastructure for you. No more Mac mini farm maintenance.
That's a massive appeal.
Definitely. The setup uses pretty straightforward YAML configuration, and it has really good built-in secrets management, which is vital for storing things like your App Store Connect API keys securely.
But there's always a trade-off. If I have a really long, complex UI test suite, what are the limitations of relying on GitHub's shared Mac runners?
That's the catch. You run into limited macOS resources, especially on the free and lower paid tiers. Builds have time limits, maybe 6 hours max per job, but free tier minutes are much lower overall. You also have limits on concurrency, how many jobs you can run in parallel.
So my 45-minute UI test suite might hit a wall.
It might hit the time limit, or you might exhaust your included minutes quickly, forcing you onto more expensive plans. Or you'd need to get creative with parallelization, or maybe even self-hosted runners connected to Actions. Also, for some really complex niche iOS build requirements that need specific tooling installed, it can sometimes feel a bit less mature or flexible compared to platforms designed only for mobile.
Okay, so speaking of platforms designed only for mobile, let's talk about the specialist. Bittrace. They market themselves as solving mobile-specific pain points out of the box.
Bittrace is definitely carved out a niche as being mobile first. It's cloud-based, like GitHub Actions runners, but its entire interface and feature set are geared towards mobile devs, iOS, Android, React Native, Flutter, etc.
What makes it mobile first in practice?
It provides hundreds of pre-built steps. These are like reusable actions or plugins, but they're specifically tailored for common mobile tasks. Running Xcode builds, managing CocoaPods, handling Android signing, uploading to TestFlight, interacting with Firebase app distribution. This means you often write much less custom script code.
Less YAML wrangling.
Potentially, yes, especially with their visual workflow editor. You can drag and drop these steps to build your pipeline, which makes it very accessible, particularly for teams or individuals who aren't CI/CD experts or don't love YAML. And one of their standout features is automatic code signing. They have systems designed to help manage and automatically sync your iOS certificates and provisioning profiles, which, as we know, is a huge pain point.
Okay, that sounds appealing, but wait. If you're relying heavily on their visual editor and their specific pre-built steps, aren't you just trading configuration complexity like writing YAML for a different kind of complexity, namely vendor lock-in? Is that convenience worth the potential lack of portability?
That is an excellent and very fair critique. Yes, there's definitely a degree of lock-in with the visual editor and the specific Bitree step ecosystem. For a small team that values speed of setup and ease of maintenance above all else, that trade-off might be perfectly acceptable, even desirable.
Oh, for larger companies.
For larger enterprises or teams that need extremely custom-built logic or have strict requirements about portability between CI systems, that cloud dependency and the potential for less control over the underlying build environment compared to, say, Jenkins could be a drawback. And of course, as your usage scales up, more build minutes, more concurrency, the cost can become a significant factor compared to some other platforms.
Makes sense. Okay, one more major player. Circle CI. This one feels like a general-purpose CI/CD powerhouse, but with strong capabilities for iOS too.
Yeah, Circle CI is very popular across web and mobile. Like GitHub Actions and Bitrise, they offer powerful Cloud Mac-O runners, so you avoid the hardware management pain of Jenkins. Their strength lies in providing incredibly flexible workflows defined via YAML, similar to GitHub Actions. But where Circle CI often stands out, especially for complex testing scenarios, is its support for advanced parallelization, particularly matrix builds.
Matrix builds, how does that work?
Let's say you have a UI test suite that takes maybe 20 minutes to run sequentially on one simulator. With Circle CI's matrix feature, you can define in your YAML config. Run this entire test suite job, but run it simultaneously across these 3 different configurations.
Like different devices or OS version.
Exactly. You could specify run it on an iPhone 15 Pro simulator with iOS 17 and an iPhone 13 simulator with iOS 16 and maybe an iPad simulator with iOS 17. Circle CI spins up 3 separate Mac OS environments and runs the full suite in parallel on each.
So my 20-minute test run could potentially finish in under 7 minutes, plus I get coverage across different environments.
Precisely. It aggregates the results. This directly tackles that device fragmentation challenge we discussed earlier, allowing you to get broad test coverage much faster.
That's powerful for testing. What's the downside?
Well, configuring those macOS environments, or executors, as Circle CI calls them, requires you to be quite specific in your YAML. You often need to state macos.xcode, followed by the exact Xcode version string, like 15.1.0. This adds a layer of configuration detail you need to manage, so there's definitely a learning curve to really master the YAML structure and features like matrix builds and parallelism effectively. Also, like GitHub Actions, the free tier for Mac runners is limited, so costs can increase with heavy usage.
Okay, so we've got Jenkins, control versus maintenance, GitHub Actions, integration versus resource limits, Bitrise, mobile-first ease versus lock-in, and Circle CI, flexibility, parallelism versus config complexity. It seems like no matter which platform you choose, there's one common thread, one essential tool that seems to pop up everywhere in the iOS automation space.
Fastlane. We absolutely need to do a deep dive on this. Why is Fastlane considered so indispensable? Fastlane really is the Swiss Army knife, maybe the secret weapon, for efficient iOS and Android, actually, development teams. It's an open source automation toolkit written primarily in Ruby, and it's designed specifically to integrate smoothly with Xcode and pretty much every major CI/CD platform we just discussed.
So it acts like a bridge or a common language.
Exactly. Its entire purpose is to automate all those repetitive, time-consuming, and frankly, error-prone manual tasks that are involved in building, testing, and releasing mobile apps.
Let's get specific. What are the biggest, most painful problems that Fastlane just systematically solves for an iOS developer day to day?
Oh, it hits the big ones. First, the sheer drudgery of manual builds and test flight uploads. Think about the old way. Open Xcode, select archive, wait, export the archive, choose the signing method, wait again, then manually log into App Store Connect, navigate to your app, drag and drop the .ip file, fill out the test notes.
Ugh, yeah. Easily 10, 15 minutes, and you have to babysit it.
Right. With Fastlane, you can define a sequence of steps, maybe call it a beta lane, and then just run a single command in your terminal Fastlane beta. And it handles the clean build, the archiving, the code signing, uploading it to test flight, maybe even notifying your testers on Slack all automatically.
That alone sounds like a massive time saver.
Huge. Second, and arguably even more critical, it tackles the nightmare that is code signing and certificates. This is constantly a top source of frustration for iOS teams.
The provisioning profiles, the expired certificates.
All of it. Apple's system requires this careful coordination between your developer certificates, your distribution certificates, the app's unique identifier, App ID, and the list of devices allowed to run test builds in provisioning profiles. It's complex and fragile.
So how does Fastlane help here?
Fastlane has a specific tool, a component called Match. Match aims to completely automate and centralize the management of your signing certificates and provisioning profiles.
Okay, Automate and centralize sounds good, but how does Match actually work its magic? How does it solve that coordination nightmare practically?
So, Match introduces a concept called syncing your code signing artifacts. Instead of having certificates and private keys scattered across every developer's Mac keychain and every CI build machine,
Which inevitably leads to mismatches, and it works on my machine signing issues.
Exactly. Match encourages you to store your certificates and profiles in a separate, private, and often encrypted Git repository, just for signing assets.
Okay, a dedicated repo for secrets.
Right. When a developer needs to sign a build locally, or more importantly, when the CI server needs to sign a release build, they run Fastlane Match. This command securely clones that private Git repo, pulls down the necessary certificate and its private key, decrypting if needed, uses them to sign the app.
And then, crucially,
And then, ideally, it removes those sensitive files from the local machine or CI environment after the build is done. The sensitive keys only exist temporarily during the signing process.
so it ensures consistency. Everyone uses the exact same certificate and profile from the central repo.
Yes, consistency is key. It also dramatically simplifies onboarding new developers or new CI machines. They just need access to the match repo and the decryption password, usually stored as a secure environment variable.
And what about when certificates expire or need renewal?
That's another huge win. If a certificate is about to expire, or you add a new test device, one person can run a match command, like match nuke and then match development, to revoke the old ones, generate new ones via Apple's Developer Portal API, update the profiles, and commit them back to the central Git repo. Then, every other developer and CI machine automatically picks up the latest valid assets the next time they run match. One command updates everyone.
That sounds like it turns a multi-hour error-prone nightmare into a 5-minute task.
Pretty much. It's a lifesaver for managing signing. Okay, third major problem Fastlane solves: managing multiple environments. Almost every app needs different configurations for, say, development, staging, and production. Different API endpoints, different analytics keys, maybe different app icons or names.
Right, you don't want your test builds hitting your production backend.
Exactly. Fastlane makes it really easy to manage Xcode's build schemes and configurations. You can have lanes like Fastlane Deploy Staging or Fastlane Deploy Production that automatically select the correct scheme, set the right environment variables, maybe even use different bundle identifiers before building and deploying.
So it handles that configuration switching automatically based on the lane you run.
Yep. Super useful for maintaining separation between environments.
Okay, let's quickly visualize this structure. How do you actually define these automations in Fastlane? You mentioned lanes.
Right. The core organizational unit in Fastlane is the lane. You define lanes in a file called fastfile, which is actually Ruby code. A lane is basically just a named sequence of automated steps. So you might have lane.test do.end, lane.beta do.end, lane.release do.end.
And inside the lane,
Inside the lane, you call actions. Actions are the individual commands or tasks that Fastlane performs. There are hundreds of built-in actions like Gym, which is an alias for build app, Pilot for uploading to test flight, Deliver for uploading to the App Store, Run tests, CocoaPods, SwiftLint, etc.
so a lane chains together a series of actions to achieve a specific outcome, like deploying to beta.
Exactly. We already talked about match, which is technically implemented as a Fastlane action for handling the code signing sync. And finally, Fastlane has a really powerful plugin system. If there isn't a built-in action for something you need, maybe integrating with a specific crash reporter or updating translation files in a certain way, chances are someone in the community has written a plugin for it. Or you can write your own.
So it's highly extensible.
Very. It allows you to tailor the automation to your specific team's workflow and tooling. Now, all this amazing automation, it brings us to a point of complexity that, well, no amount of tooling can completely eliminate on its own. And that's really about managing the intricacies of Apple's ecosystem security requirements, and then, crucially, closing the feedback loop after you've successfully deployed something.
Okay, let's tackle that first part, the administrative headache that just keeps coming up. iOS certificates and provisioning profiles. Even with a tool like Fastlane Match helping, why does this remain such a persistent maintenance and security challenge?
It's tough because this system is absolutely fundamental to how Apple ensures security and controls distribution on its platform. We need to be really clear on the terms first, maybe.
Good idea. Define the key players again.
Okay, you have your certificate. This is like your digital ID card issued by Apple containing a public-private key pair. It cryptographically proves you are who you say you are. There are development certificates for debugging on registered devices and distribution certificates for test flight App Store. Then you have the App ID. This is just a unique string that identifies your specific application for gcom.mycompany.myapp. And for builds that aren't going to the public App Store, like development or ad hoc builds for specific testers, you have a list of authorized device IDs, UDIDs, for the physical iPhone user pads allowed to run that build. The provisioning profile is the glue. It's a file generated by Apple that bundles these things together. It essentially says this specific app ID built by this specific developer is allowed to run on these specific devices, device IDs. For App Store profiles, the device list is effectively any device.
Okay, so it's like a permission slip linking the who, what, and where. A three-way handshake that has to be valid.
Exactly, and that validity is temporary and easily broken. That's the core challenge. First, as we mentioned, certificate expiration. Development certificates typically last 1 year. Distribution certificates last year. Provisioning profiles also expire, sometimes annually, sometimes even every 90 days for certain types like ad hoc. An expired certificate or profile immediately breaks your CI build. Signing fails.
Bam! Pipeline stops. Red alert.
Yep. And when this stuff is managed manually by different team members,
Chaos ensues.
you inevitably get code signing conflicts. Someone tries to build with a profile signed by an old revoked certificate. Or they add a new tester's device ID to the portal, but forget to regenerate the profile and distribute it. The build might succeed locally but fail on CI, or the tester gets the build but can't install it because their device isn't in the embedded profile. Manual management is just incredibly error-prone.
And what about the security angle, especially with CI servers needing access?
The main security risk revolves around the private keys associated with your distribution certificates. These keys are what prove you are authorized to release updates for your app if one leaks.
Someone else could potentially release a malicious update pretending to be you.
That's the nightmare scenario. So storing these keys insecurely, maybe checked into a public Git repo by accident, or just sitting unencrypted on a poorly secured build server, or being manually passed around on USB drives is a huge risk. The challenge is the build server needs access to that private key at build time to sign the app.
Okay, so given these challenges, expiration, conflicts, errors, security, how do we properly wrestle this beast into submission within a secure, automated CI/CD pipeline?
Two absolutely critical solutions need to be in place. First, as we dove into with Fastlane, you absolutely must automate certificate management. Tools like Match are essentially non-negotiable for mature teams. By centralizing the certificates and profiles in a secure encrypted repo and having both developers and CI servers pull from that single source of truth, you eliminate the consistency errors and drastically simplify renewal.
So automate the sync using something like Match. What's the second piece?
Second, and this applies to all sensitive data, not just signing keys, use environment variables and secrets management. Your distribution certificate's private key password, if it's encrypted, your App Store Connect API key needed for uploads, any sensitive API keys your app uses, none of this should ever be hard-coded directly in your fast file or your project source code.
Where should they live then?
They need to be securely stored on the CI server itself, using the platform's built-in secrets management features, like GitHub Secrets, Bitrace Secrets, Circle CI contexts, Jenkins credentials. Then, during the build process, the CI server injects these values into the build environment as environment variables. Fastlane and your app code can then read these secure values from the environment.
So the secrets live securely on the CI platform, are injected only when needed, and never touch the source code repository.
Exactly. That isolation is crucial for security.
Okay, that makes sense for securing the build and signing process. Now, let's say the pipeline runs, the app is built, signed securely, and automatically deployed to our testers via test flight using Fastlane. What's next? The team needs to know immediately if that new build is stable, right? This brings us to closing the feedback loop with crash reporting. We flag two big players, Firebase Crashlytics and Sentry. Let's start with Crashlytics. What's its main focus? Firebase Crashlytics, which is part of Google's Firebase suite, has historically been laser-focused on, crash reporting for mobile apps, primarily iOS and Android. Its core job is to capture crashes in real time when they happen out in the wild on user devices. What kind of information does it give you?
It gives you the essentials for debugging. detailed stack traces showing exactly where in the code the crash occurred, information about the device, model, OS version, orientation, memory available, and context like which view the user was on. But perhaps its most powerful feature for teams is its crash prioritization. Crashlytics automatically groups identical crashes together and tells you not just how many times a crash happened, but critically, how many unique users were affected by it.
So you can focus on the issues hitting most people first.
Precisely. A crash that happens 100 times but only affects 2 unlucky users might be less urgent than a different crash that happens only 50 times but impacts 50 different users across various devices. It helps you triage effectively based on real-world impact.
Okay, so Crashlytics is the mobile stability specialist. Great for prioritizing fatal errors based on user impact. How does Sentry fit into the picture? Does it do something different?
Sentry positions itself as a broader error tracking and performance monitoring platform. While it definitely does excellent mobile crash reporting, similar to Crashlytics, its scope is much wider. It's designed to work across your entire stack: mobile front ends, web front ends, back-end services, even desktop apps.
So a more unified view.
Yeah, often. But the key difference in functionality is that Sentry puts a significant emphasis on tracking non-fatal errors and providing deep performance monitoring insights alongside the fatal crashes.
Non-fatal errors, like what?
Things that don't necessarily crash the app but still indicate a problem or provide a poor user experience. Maybe an API call failed gracefully but took 10 seconds. Maybe a handled exception was caught, but it indicates a logic flaw. Maybe the UI thread became unresponsive for a few seconds, an application not responding, or ANR event. Sentry aims to capture these soft failures too.
And performance monitoring.
Sentry can track things like slow screen loads, high latency API calls, excessive UI rendering time. It provides breadcrumbs, a log of events like user taps, network requests, view changes that happened before an error or crash occurred, giving you much richer context for debugging. If a slow network request eventually leads to a UI freeze and then a crash, Sentry might help you connect those dots, whereas Crashlytics might only show you the final crash point.
Interesting. So if we had to draw a direct comparison, Crashlytics versus Sentry, what's the key strategic takeaway for a team lead choosing a tool?
Okay, simplifying a bit. If your primary, maybe sole concern is purely the stability and fatal crashes of your native mobile app, iOS, Android, and you want something often considered very easy to integrate and focused on that core task, Crashlytics is excellent and often free via Firebase. However, if you want a more holistic view of your application's health, including performance bottlenecks and non-fatal issues, or if you need to monitor errors across multiple platforms, mobile app plus backend APIs, in one place, Sentry provides that broader coverage and deeper context. It often has more powerful filtering and analysis tools, but might have a steeper learning curve and potentially higher costs depending on your event volume.
Got it. Crashlytics for focused mobile crash stability, Sentry for broader error and performance monitoring, potentially across platforms. Now let's bring this back to the practical flow of the CI/CD pipeline. A really common and valuable application is automating test flight distribution. We've built the app, signed it, maybe run some tests. Why is automating that final step, getting the build onto testers' devices via test flight, so incredibly valuable?
It comes down to speed and reducing friction, really. Manual uploads are just a bottleneck.
How so?
Without automation, a developer, a QA person, a release manager has to manually stop what they're doing, probably find the .ip file from the CI server, or build it locally, log into App Store Connect, navigate through the menus, upload the binary, wait for Apple to process it, which can take anywhere from 5 minutes to an hour sometimes.
And then manually assign it to the right testing groups and maybe write release notes.
Exactly. It's easily a 10-20 minute manual context switch involving waiting and clicking every single time you want to send a build to testers. And if you're doing true continuous delivery, that might be multiple times a day.
That adds up fast.
It really does. Automation, typically using a fast lane action pilot or a dedicated step in your CI platform, like Bitrus's test flight step, completely eliminates this. The moment a build from, say, your develop branch successfully passes all the CI checks, builds, tests, the pipeline automatically triggers the upload to test flight, assigns it to the predefined internal testers group, maybe even pulls the latest commit messages to use as release notes.
So testers get new builds almost immediately after the code is merged and verified.
Yes. It ensures that every potentially shippable build is delivered promptly to QA or stakeholders. It reduces human error, like uploading the wrong build or forgetting a step, and drastically shortens the feedback loop. The delay between code is done and merged, and QA can start testing shrinks from hours or days down to minutes. It's all about maintaining development velocity.
That makes the whole process sound incredibly smooth, almost effortless when it's set up right. But, reality often bites. Let's talk about troubleshooting. Let's walk through a common, really frustrating scenario. A user reports a random intermittent crash. Say your app sometimes crashes when they're scrolling through a complex UIable view with lots of images and data. How would a development team leverage this mature mobile DevOps infrastructure we've built, the CI/CD, the monitoring tools, to actually investigate and fix that kind of nasty random crash?
Yes, the dreaded random UIable view crash. That's a perfect test case because these intermittent issues often point to more fundamental problems like memory management or threading, not just simple logic bugs. The investigation process, using a good DevOps setup, becomes much more structured and data-driven. Step 1, try to reproduce the crash. This is always the first hurdle. Random isn't helpful. You need to verify it exists and try to find conditions that make it more likely. Since scrolling complex tables often stresses memory and the main thread.
You'd focus your testing there.
Exactly. You'd specifically try testing on simulators configured with low memory warnings enabled, or better yet, on older physical devices have less RAM or slower processors. Maybe try scrolling really fast, or scrolling while background tasks are running. The goal is to find some sequence of actions, even if it takes a few tries, that reliably triggers the failure. You need a reproducible case.
Okay, can't just rely on the vague user report. Let's say you managed to reproduce it, maybe on an older iPhone 11, after scrolling frantically for 30 seconds. What's next? Where do you look first?
Step 2, check the crash logs. Immediately dive into your crash reporting tool, Crashlytics or Sentry. Filter for crashes related to the version you were testing. The crash report is your primary source of truth.
What are you looking for in the log?
You're looking for the stack trace. This tells you the exact sequence of function calls leading up to the crash. Often with table view issues, it might crash inside UIKit code related to cell reuse, reusable cell, data source methods, cell foreup, or maybe even something lower level like memory access, objcmsg send, or a Swift runtime error. Critically, the report also tells you the device model, OS version, memory state, so is it low, and maybe even custom logs or breadcrumbs you added. This helps narrow the scope significantly. It turns a random crash into, say, exibit access crash in tableview.cell48, specifically on iOS 16 devices when memory is constrained.
Okay, the logs pinpoint where it's failing. But if it's intermittent or tied to scrolling, that suggests it might not be a simple coding error, but maybe a resource issue.
That's a very common scenario. Which leads to step 3. Identify memory issues. If the crash seems random, happens during intensive operations like scrolling lots of bait images, and especially if the crash logs mention memory warnings or exibit access, often related to accessing deallocated memory, then memory pressure is a prime suspect.
How do you track that down?
You break out Apple's Instruments tool, which comes with Xcode. Specifically, you'd profile your app using the allocations and leaks instruments while performing the reproducible steps, that frantic scrolling.
What are you watching for in instruments?
You're watching the memory usage graph, the heap. Does it just keep climbing steadily as you scroll without ever going down significantly when you stop? That suggests you're allocating objects but never releasing them a memory leak. The leaks instrument can sometimes pinpoint specific objects that have been leaked. You're also looking for sudden spikes in memory allocation when cells are created. Eventually, if the app consumes too much memory, the OS will terminate it. That's your crash. Step 4. Optimize table view performance. Assuming the crash is related to the UIable view, which is common, you then need to review the implementation against best practices, specifically looking for things that cause excessive memory use or main thread blockage during scrolling.
Like what specifically?
The absolute number one thing is ensuring correct cell reuse. Are you always calling decureusable cell with identifier.forCell? If you're creating new cells from scratch every time instead of reusing them, memory usage will skyrocket.
Okay, reuse is crucial. What else?
Avoid doing heavy work synchronously inside tableview.cell4rows. This method gets called frequently during scrolling and needs to be lightning fast. Any complex data processing, filtering large arrays, resizing images, making network calls, that stuff must be done asynchronously on a background thread. Images, in particular, should be loaded lazily and asynchronously, maybe using libraries like SD-WebImage or Kingfisher. Keep cell4row focused only on configuring the cell with already prepared data. Step 5. Hunt for retain cycles. This is another common source of memory leaks in iOS, especially with Swift closures. A retain cycle happens when two objects hold strong references to each other, so neither can ever be deallocated by the automatic reference counting (ARC) system, even if nothing else in the app is using them anymore.
Where do these typically hide in table view scenarios?
Yeah. Often in closures used for asynchronous operations within the cell, like that image loading we just mentioned. If a cell has a closure, like a network completion handler, that captures the cell instance strongly, and the cell itself also holds a strong reference to whatever owns that closure, you can create a cycle. The cell and the closure keep each other alive indefinitely, leaking memory every time a cell is scrolled off screen but not properly deallocated.
Okay, so how do you practically fix those closure-based retain cycles? What's the code look like?
The standard fix is to use a capture list at the beginning of the closure definition. Instead of just .code using self, you write weak self in .code using self, or sometimes unowned self in .code using self.
Weak or unowned? What's the difference?
Weak self is usually safer. It makes the closure hold a weak reference to self. Inside the closure, self becomes an optional self, so you need to safely unwrap it, for example, guardlet strong self, else return, before using it. This breaks the cycle because the closure doesn't keep the cell alive. Unowned self also breaks the cycle, but assumes self will always exist for the lifetime of the closure. If self could potentially be deallocated before the closure runs, using unowned will cause a crash. So weak is generally preferred unless you're absolutely certain about the object lifetimes.
Okay, so use weak self enclosures, capturing self to break potential cycles. Makes sense.
Step 6. Test thoroughly and redeploy. Once you believe you've found and fixed the issue, maybe you fixed cell reuse, moved image loading to the background, and added weak self to a closure, the developer commits the code.
And the DevOps magic kicks in?
Exactly. The commit triggers the CI pipeline. It automatically builds the fix, runs all the unit and UI tests. Assuming those pass, and maybe you add a new test specifically for this scenario, the pipeline automatically builds the artifact, signs it using match, and deploys it via pilot to the internal testers group on test flight.
Fast feedback on the fix.
Super fast. QA can then immediately grab that build and specifically try to reproduce the crash again on those problematic older devices under simulated memory pressure if possible. They verify the fix hold across different OS versions. Only once verified does it get merged and queued for the next proper release.
That's a great walkthrough. It really shows how the culture, the pipeline, the tools, and the monitoring all work together to tackle even tricky issues.
Absolutely. If we sort of synthesize this whole journey we've been on today, we've really connected that strategic, cultural idea of adopting DevOps, this mindset of continuous verification and improvement, to the practical, technical infrastructure needed to support it, the CI/CD pipeline blueprint.
And we've armed that pipeline with specialized tools, especially Fastlane for the automation glue, and things like Crashlytics or Sentry for that critical real-time feedback from the wild.
Right. The ultimate goal, the outcome of this whole transition, isn't just about pushing releases out faster, although that's a benefit. It's fundamentally about embedding quality throughout the process, minimizing the risk of regressions or failures reaching users, and giving teams the ability to rapidly diagnose and fix the complex problems that inevitably crop up in real-world mobile app usage.
It sounds like it transforms development from periodic, stressful release events into a more continuous, predictable flow.
That's exactly it. By automating almost every manual step from compiling and running tests, to managing those awful certificates, to deploying builds to testers, you enforce consistency, reduce human error, and maximize the speed at which high-quality, stable code gets into the hands of users and provides value. That continuous feedback loop, powered by automation and monitoring, is what makes modern, complex mobile development manageable at scale.
And as we've explored, that feedback loop is becoming increasingly sophisticated. It starts with the CI server's immediate pass-fail right after a commit, extends through automated testing, and closes with detailed crash reports and performance metrics coming back from tools like Sentry or Crashlytics almost instantly after deployment.
We've seen how tools like Fastlane, particularly Match, have done a remarkable job of automating away some of the most painful manual steps, especially around certificates and provisioning profiles, things developers used to spend hours wrestling with.
They abstracted away a lot of that cryptographic complexity, even though the underlying Apple system is still there.
Right. It's currently the peak of practical automation for that specific problem, but it still requires the developer, or at least the team's CI setup, to explicitly manage, generate, store, and sync those cryptographic assets, even if Match makes it easier.
So building on that, here's a final thought for you, the listener, to mull over as you think about where this is all heading. We're seeing the CI/CD landscape rapidly shift towards deeper cloud integration and higher levels of abstraction, trying to hide even more of the underlying infrastructure from developers. If tools like Fastlane Match have already figured out how to automate the generation and synchronization of certificates using APIs and secure Git repos.
Yeah, abstracting the manual pain away.
What kind of future automation, perhaps driven by even smarter AI orchestration layers within cloud-built platforms, might eventually make the entire concept of manually dealing with certificates and provisioning profiles completely invisible to the application developer? Could we reach a point where code signing just happens automatically and securely as an encrypted handshake between the authenticated build server and App Store Connect, without the developer ever needing to explicitly generate, download, or manage a .p12 file or a mobile provision profile ever again?
That would truly be the final frontier, wouldn't it? Removing that last, stubborn layer of cryptographic plumbing completely from the developer's direct concern. A fascinating possibility.
Something to think about.
Yeah.
Thank you so much for joining us on this deep dive into the architecture and practice of mobile DevOps for iOS. We really hope this gave you the detailed, practical knowledge you need to better navigate the world of automated mobile releases.
Yeah, hope it was useful. Until next time.